Hello, this is Mr. Gilmore with the 7.3 side angle side and side similarity. Now, what's going to happen in this lesson is we are going to forego the proofs of side angle side and side similarity because they are nearly identical to the proof of angle angle similarity. So the way this lesson is going to be broken down is we're going to first introduce the side angle side similarity, what it states, and we'll do several examples with using that. And then we are going to jump into side similarity, talk about the follow-up, and then again state the fact that we are not going to prove this. We'll talk about what the proofs will look like, but we are not going to walk through the full proofs of side angle side and side similarity. So to begin, let's go ahead and state what is the side angle side similarity theorem state. Again, this is a shortcut to similarity, right? This is another way for us to show that we don't need all the pieces of information to show two triangles are similar. We're going to take a shortcut in it. Here's what it states. If two sides of one triangle are proportional to two sides of another, and the included angle of the first equals the included angle of the second, then the triangles are similar. So here's a quick illustration then of what side angle side similarity that take that conditional and actually bring it to life. What we're saying is if we're given two triangles ABC and RST, such that if we were to pick two pairs or two sides of the first and two sides of the second that correspond, and they are in fact proportional to each other, and that they have an equal included angle, which means the angle that's sandwiched between those proportional sides, then we can call the two triangles similar. And this is a shortcut. So we don't need, again, to know all angles are equal or all sides are proportional. All we need is the side angle side pattern, and we can then produce similarity between the triangles. So again, think about what this means when we find two triangles to be similar. There's an immediate follow-up to that. So what we know to be true then about these two triangles below, that if we assume that AB and ratio to RS is equal to BC ratio to ST, and the two angles that are included are equal, then yes, we know these two triangles are similar. Well, then from the definition of similar, right, as we dig into the similarity of the two triangles, we can follow up with what do we know about the other corresponding sides and the other corresponding angles. Well, the other corresponding sides are obviously going to still be then proportional to the two pairs of sides that we established from our given of these two triangles, that we knew two sides of one triangle were already proportional to two sides of the other, which means we can grab the third pair of sides and say, well, that's the same ratio. They're going to be proportional to all three sides. And then we have what follows up about angle A is that it corresponds with angle R, and that means we can call the measure of angle A equal to measure of angle R. We know all corresponding angles must be equal. And same story with angle C, we can call that equal to its corresponding angle, angle T. So remember, shortcut to similarity is just as powerful of a tool as congruence because it gives us more information about our triangles, and then we can use that more information to either find a given solution or use that to carry us into another conclusion about two triangles. So let's actually use side angle side similarity to answer a few questions. So the first thing is to find the values of the variables in the diagram below. So we're looking for two missing variables. You can see in the diagram there's an x variable is missing that represents a side length, and a y variable missing representing the measure of an angle. What we're actually going to do is first let's prove that these two triangles are similar, and once we know these two triangles are similar, we can then begin finding these missing angle or these missing variable measures. Okay, so why do I know these two triangles are similar? So the very first thing I notice is that we do have this right angle where these two angles or these two triangles are kind of joined here at this vertex down here. So because that angle is right, we know then the angle next to it is also a right angle, which then gives us a pair of equal angles. And not just that, but that pair of angles is going to be a pair of included equal angles here as we find our proportional sides. Next thing I notice is that there is a point here that where our first triangle, or kind of the hypotenuse of our little small triangle meets at the midpoint of the larger triangle there, which means there is a ratio going on between those sides. If I were to think about what the measure of this side here, of the smaller side here, it's half of this, which means there's a ratio from this midpoint of 1 to 2. Okay, so there's a ratio of 1 to 2, all right, from my smaller to my larger. Well, then, if you notice with the other sides given, I have this 1.5 and this 3. Well, notice that if I were to form a ratio of 1.5 to 3, right, form a ratio of these guys, it also produces a ratio of 1 to 2, which means I do have two sides of one triangle proportional to two sides of another. And the angle between them, the included angle, are those right angles, which means we know that the included angles are in fact equal in measure. So we've got ourselves similarity between these two triangles, and because of that, we can match up corresponding parts, and we can also create proportions with our sides and solve for missing side measures. So let's start with our measure of y first, our variable y. That's going to be the easiest one. The value of y is actually 36. Why? Because all corresponding angles are going to be equal, which means the measure of 36 degrees from our larger triangle is going to be equal to the corresponding angle y in our smaller triangle. So finding the variable y is very simple, right? All corresponding angles are equal. Because I know the two triangles are similar, I can tap into the definition of similarity. Now I'm on to find the measure of x. And in this case, I am going to have to set up a proportion, okay, to solve for x. So I already know what my ratio is. My ratio is 1 to 2, right? Going from my smaller triangle to my larger triangle is a ratio of 1 to 2. I get that same ratio if I were to do the 1.5 over 3 or set up the midpoint from the side that we have there. So that means I have 1 to 2 is the same ratio as x to 5, and then I can then cross multiply and solve for x. So I get 2x is equal to 5, and then divide both sides by 2. We get x is, we can write that as an improper fraction, 2.5. We are already dealing with a terminating decimal there, so I would feel comfortable with just re-expressing that as a decimal as well, so 2.5. So either one of those I would feel comfortable already because we had the 1.5 decimal given to us. But there we have it, finding the missing values of our x based on the side angle side similarity shortcut that we have between triangles. Let's continue that side angle side into this example here. Now, this is an interesting example. It says, are the two triangles in this diagram below similar? So again, the question is, can we prove them to be similar? And in this case, we're going to have to check two ways. All right, I'll explain what that in a minute. The first thing is when I compare the ratios of my sides, I need to know from my smaller triangle to my larger triangle, which means I need to know the smaller length to the entire length of the larger side, which means I'm going to take my 8 and 4 here and add them together to say I know the entire side length BC is 12, and then I'm going to take the sides here, 6 and 10, add them together, the entire length of AB is 16. So a natural approach to this is go, okay, let's start making some ratios out of these corresponding sides, and let's see if we can find these sides to be proportional to each other. So the natural kind of reaction is go, oh, let's make a ratio of 6 to 16, right? It'd be BE ratioed with AB, which means then let's test that against BD to BC, so it'd be 8 to 10. 8 to 12. That's kind of the natural reaction of like, let's just ratio those guys together. So the question is, are these two ratios equal? Well, they're not, right? If you even simplified them, you get 3/8 is equal to 2/3, and no way are those the same value, okay? So those are not the correct, those sides are not proportional, right? Because they don't form this true proportion. But the question we have to ask ourselves is, well, maybe BE, we were focused on BE corresponding with the side AB. Well, what if BE doesn't correspond with that side? Right? BE is the smaller part of the smaller triangle. What if it doesn't correspond with that side of the larger triangle? What if it corresponds with the other side of the larger triangle of the side BC? So let's check out a second ratio. What if BE 6 corresponded with BC, which is 12? And that means our smaller side of our triangle BD, which is length of 8, maybe that corresponds with the other side of the triangle, AB, which is the length of 16. So now the question is, are those ratios the same? Is this a true proportion? And it is. When we reduce these, check, look at that. We do actually have proportional sides. Now, so notice that BE didn't correspond with the side that it was on, that's a part of. It corresponded with the side it's not a part of, right? The other side of triangle ABC. Well, what that means is we do have proportional sides, right? Two sides of one proportional to sides of the other, and these two triangles do share the included angle B there, which means we do have side angle side similarity. And what I want to do real quick is just go ahead and write out the similarity statement here for these guys, because it's be interesting to see how the similarity statement unfolds. If I start with ABC as my the larger triangle here, started out with my similarity statement, triangle ABC, I would then have to conclude that angle A doesn't correspond with the angle BED. It actually corresponds with the angle BDE, which means it would go DBE is its corresponding corresponding parts within those two similar triangles. And so that would be the similarity statement writing this out. So are the two triangles similar in this diagram below? Yes, they are. By, again, side angle side similarity. That's our new shortcut into similarity, okay, using side angle side. One last little bit with side angle side. We have seen this theorem already back in semester 1 when we talked about the midsegment theorems. This is known as the triangle midsegment theorem. Two fascinating things again happen with a midsegment. Recall that a midsegment is if we form the midpoints of two sides of a triangle and join them with a segment. That segment formed is known as a midsegment of a triangle. And that midsegment actually does two phenomenal things. The first thing is that it is parallel to the side it doesn't intersect, and it's also half the length of the side it doesn't intersect. Now, we saw this in first semester, and it required a lot of kind of ingenuity and some creativity with our constructions to arrive to these two conclusions. However, now with side angle side similarity sitting around for us to actually use, it shows that the proof of the triangle midsegment theorem is actually a piece of cake. Walking into this one, trying to find these two conclusions that DE is parallel to AC and that DE is half the length of AC. It's actually quite simple. I'm going to guide you through this one on the worksheet, but just kind of give you a heads up of what you're going to be seeing. The first thing is you will be using side angle side similarity to prove that these two triangles, triangle ABC, is actually going to be similar to triangle DBE. Okay, that's actually the first thing you're gonna figure out is that those two triangles are in fact similar with side angle side. So in order to use side angle side, you have to consider, well, what do we need? We need a pair of included angles that are equal. Okay, so we've got that, right? Angle B is shared between the two triangles, so we've got the included angle. Check, that's easy. But then we need to show that two sides of one triangle are actually proportional to two sides of the other. Well, think about what D and E are. They're both midpoints, which means point D is cutting our entire side of AB into a ratio of one part to two parts, right? One to two. So we know we have a ratio of that one side of 1 to 2. Well, what's happening on the other side? It's also cutting into a ratio of 1 to 2. So we have the same ratio for those two sides, which means we do have proportional sides. That BD to AB is the same ratio as BE to BC. So we do have two sides of one triangle proportional to two sides of the other, which then leads us right into side angle side similarity, and that leads us into triangle similarity, and we can tap into the definition. So remember, from the similarity that you're going to find here, you know several things. You know that all the corresponding angles are going to be equal, and you know that all the corresponding sides are going to be proportional. So keep that in mind as you go through the triangle midsegment theorem on the worksheet. And I guide you through that one a little on the worksheet, kind of giving you some advice on step-by-step where to go with that. Okay, so now we turn our attention to the end of our lesson by looking at side similarity. This one's pretty straightforward. There's no really beating around the bush here. It's just dive right in this one. This is actually pretty straightforward. As I said, if the three sides of one triangle are proportional to three sides of another, then those triangles are in fact similar. And so again, a third shortcut into similarity with the side similarity statement. So what immediately follows, here's a quick illustration of our side similarity. We're given two triangles. Now again, the two triangles, we don't know anything about their angle measures, but we do know from the given that all three sides are proportional to all three sides of the second, which means if we set up those ratios of corresponding sides, all three of those ratios will be equal to each other. So we have if AB over RS is equal to BC over ST, which is equal to AC over RT, then the two triangles are in fact similar. So again, what can we draw from similarity? Well, now we know something about the angles of these two triangles. We know all three sides are given to us as proportional, which means then all three corresponding angles are equal in measure, because we can tap again into the definition of similar. So just keep that in mind as you approach this worksheet for side angle side and side similarity, that you will be using both of those, and also be on the lookout for angle similarity. That's kind of worked its way into that worksheet as well, utilizing all three of our shortcuts of similarity. So be on the lookout for these ways to show two triangles are in fact similar using any of these three theorems. And what that's going to require you to look out for are equal angle measures. How do I set up ratios of sides? Maybe you need to play around with the choice in which sides to ratio, right? Which sides do you choose to then correspond with others? Because you may have to play around with finding the correct corresponding sides. So there's some issues. There's going to be some digging involved in finding the similarity between the two triangles. And last but not least, again, I just want to remind you one more time that the proofs of side angle side and side 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 similarity, we are going to forgo. We're going to skip these proofs, which means if you ask me, hey, are you going to throw these at us later on? No, I will not be asking you to prove side angle sides or side 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 similarity on any assessment, any homework assignment. They really are identical to the angle similarity. Here's how we would do it. We construct a third triangle such that it's similar to one and congruent to the other, and then we can build similarity between those two triangles using that theorem we proved on a previous worksheet. So the proofs, yep, we're not going to do those side angle side nor side side side. So don't ask me, are we going to do those later on? Nope, nope. Not going to be tested over, not going to be assessed over. We're skipping those proofs. All right, so we're at the end of our lesson here with our side angle side and side 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 similarity. Be sure to be working on that worksheet. And again, if you come across any questions you need help on, email me and I'll get back to you. With that, be good and do good.